But before we get started, the order is up there. We do have the banquet information here. Most of you have already RSVP'd, but just in case you didn't and you talk to me, please just show up there at 6:30. Great. So our first one is Anupam Gupta, and your 4 minutes starts now.
Oh gosh. Okay, so I'll talk about learning online algorithms. And I was thinking about this, Avram's 60th birthday, what do I talk about? And these are both topics that I learned from Avram, and not maybe directly from him, from his lecture notes. So if you want to learn about these things, you should find these old PostScript slides, including the one from Lipari that John was just talking about. And there are all these sort of cool results out there. You learn a lot. I learned a lot. So at least I can speak from experience. So what am I going to talk about? I'm going to talk about learning online algorithms. And it's kind of a cute little thing that we did. Okay, so I want to do online load balancing. A bunch of jobs arrive over time. Whenever a job arrives, it tells you which machines it can go to. You want to assign the job immediately to that machine or to one of the machines. Minimize the maximum load. Okay? Okay, what do we know for this old problem? There exists a log comparative algorithm. M is the number of machines. There exists a log load bound. So the problem is solved. Okay. So how do we go beyond? And this is another topic that Avram and I have talked for a long time. Beyond worst case analysis. So here's a model that came up. We're trying to do model algorithms with predictions. And there's a question of where do these predictions come from, and there's a lot of discussion about this. I won't get into the philosophical discussion, I don't have time. I'll just tell you the model that's there. The adversary fixes an online instance I. It's a sequence, okay? What do? Today you get to see a sample. You get to see a random Q fraction of I, 1% of I, okay? You can use this to learn a good algorithm for tomorrow, where you'll actually see the requests coming online, one by one. And it's really, this audience, I don't need to sort of motivate this too much. By the way, there's no distributional assumptions on the instance itself. It's a worst case instance. This model actually was, I learned it from a paper of Kaplan, Nauri, and Raz, but it actually goes back to early work in the 80s. And really, it's sort of there's a learning question out here. The sample is the training data. You want to use this to learn a good strategy, which should generalize. No surprises again to this audience out here. But what can you say for this problem that I'm interested in? So what I can say is I can say something like this. We can achieve an algorithm with load 1 plus epsilon. Epsilon is a parameter you can choose. 1 plus epsilon times opt plus some term which depends on the sampling rate and this log over epsilon. Okay? How do I think about it? I basically think about it as when opt is large, you can get a very good estimate of opt. In the worst case, this is not possible. The lower bound I showed works for arbitrarily large opt. Okay? So here, basically, if opt is large, somehow you can learn from the sample. And you can get an algorithm that learns. So maybe, instead of, giving a whole talk, I'll give you a sense of how we do this. And there are 3 ideas. The first is a trivial idea, almost. If opt is large, then a fractional assignment is almost as good as an integer assignment. And what's the proof? It's a Chernoff bound. Okay. So you've already got 1 out of 3. That remains, leaves 2. The second one is a very cute idea. It's not an original idea. It's something we learned recently. There exist machine weights. So let me give you an example. There are machines. There is an instance. Okay? You fix an instance. Then I can give you these weights, 1 for every machine, such that when a job comes, it looks at the machines it can go to. And it will, the weights of these machines are 1, 2, and 4, let's say. It can just fractionally assign itself proportionally. And the theorem says there exist these weights such that this proportional assignment is pretty darn good. Okay? How do you prove this? you prove this using convex duality. You write down some convex optimization problem and show that the duals give you these weights. Good. So that leaves the third piece. All this is about load balancing. I haven't told you anything about samples and stuff like that, right? So the third piece is actually says there exists an algorithm to learn these weights from the small sample. And really, I need something to be able to generalize this thing. Perfect. And how do you do this? You do this from the technique I learned from Avram, multiplicative weights, and also some ideas from parallel algorithms, which is perhaps the new idea out here. So in any case, let me stop here. Little learning goes a long way. And, OK. And I'll end with a little picture I found. Took me some doing. This is from the old days, I think 2005, where John was actually visiting us. And anyways, I'll stop at that.
30 seconds for a question while the next speaker sets up. If you have any pressing question.
Was it being hung? That's actually Null Simon. Oh, okay.
So the weights, the number of weights is relatively. It just depends on the machines, not the number of joints. So that's
exactly.
So that's what's kind of.
That's exactly it.
Okay,
There's a small representation that you can learn from the sample.
Which one?
Okay.
All right, our next speaker is Kevin Stangl.
Hey guys, thank you. Happy birthday, Avram. It's been a little bit while since I proved a theorem, so I wanted to have this talk be a sort of very high level and maybe a call to action for this lovely theory community. And my question, I've been thinking a lot about this phrase from this memo by Vannevar Bush that I'm sure many of you are very familiar with, arguing why the American government should invest in scientific research endlessly, the endless frontier that we have models, we have technology, we solve problems. Beyond that, there's more problems, and they sort of generate these good social outcomes downstream. And maybe just because I live in, also I should say, everything in here is my opinions only. Definitely do not associate them with my employer or anyone else. Don't blame Avram. But maybe because I live in San Francisco, I feel like there's this kind of milieu among researchers and engineers and just people on the street that this endless frontier, it's maybe gone, it's ended. Vannevar Bush is wrong. And we're in this new paradigm where we're not going to, AI is sort of somehow the final technology, the final scientific paradigm. And, we're going to replace theoreticians and these gadget constructions with AlphaEvolve. And I use AI constantly in my own work, as I'm sure many of you do. I heard some eavesdropping that some well-known theory researchers are maybe, shifting their work somehow. And I just don't know. Is this true? Is it not? How do we respond to this? And it seems like it should be a good theory question. And again, there's just this vibe where this current AI paradigm of sort of pre-train on everything, doing some kind of RL is just going for any task that is computable in some broad natural sense. And also, everything I say here is super vague, and I would love it to be more formal. Maybe you guys will write the paper, or maybe I will. And is this good? Is this bad? And I'm generally not sure. I'm generally pretty optimistic, I think, but I would really like a formal, kind of crispy sense of that. And why? We're allocating a lot of resources in this one kind of research direction. It'd be good to figure out if we should go in other directions as well. And maybe what do we need? And as I was getting this talk ready, I was looking at some of the speakers, and I realized for some of my little bullet points, you guys have papers with these titles. I think, John Kleinberg, you have a paper with a very similar title to this from a year or two ago. Do we need new complexity notions? Do we need new models of learning that kind of poke at the boundaries of this very broad next token prediction paradigm? I think papers in each of these would be great, but what I would really like is something else, and it would be something Avram-esque, where I feel like when we were working together, and also in some of Avram's previous papers, you'd have these little atoms of understanding that just felt very truthy to me in this kind of not brittle sense that I think some theory papers sometimes are. And I think this sort of current LLM AI paradigm has some of these limits. I don't know where they are, and I would love to find out. And I got to end on the Avram appreciation slide with my last 30 seconds, which is, Avram, I have some faith that you will find some of these boundaries on this endless frontier. So proof by Avram, I hope. And thank you, guys.
Or comment?
Or fighting words.
As you introduced, it would be nice if you also present, like, if you were a Avram student. I guess I don't know what the speakers.
Then introduce
Oh,
yourself.
I was Avram's student. I'm now graduated. My employer is unknown because they should not be affiliated with my comments.
Maybe from now on.
And I'll give Kavya an introduction. Kavya is Avram's most recently graduated student as of 1 week ago.
All right. Now we have Kavya Ramachandran, yeah.
Hi, maybe? It's off. Okay, hi. Today I want to tell two stories. One is about a problem with connections to a whole bunch of people in this community, and the second is about Avram as an advisor. So I want to tell you about the Improving Multi-Arm Bandits problem, which was formalized in 2016 by Haydari, Kearns, and Roth. And so this is a problem where each time you pull a bandit arm, you get some sort of reward. That's a function of how many times it's been pulled so far. And this is a nice way to, model things like hyperparameter tuning or kind of trying to decide between different technologies that you're trying to develop. And a lot of people have studied this, both in terms of giving regret guarantees as well as competitive ratio guarantees, including us. And so one thing we've done is given this worst case near optimal algorithm, where the strategy is something like you try everything for a bit and you make a good guess about what's achievable, and then you only work on things that will help you get there. And that gives you a nice competitive ratio bound between square root k and square root k log k, where k is the number of bandit arms. And we've also looked at data-driven guarantees for this problem. So you get some collection of improving bandit instances sampled from some distribution. And if you have some family of algorithms from which you want to learn a good algorithm, we can give a sample complexity bound. And so here's a very partial list of open and related problems. So this is the problem that we studied. But you can think of changing the structure of the reward or the feedback model or introducing some sort of cost to play the option. And this is also pretty closely related to problems like the Pandora's box problem and some extensions and generalizations of that, which I think we'll hear a bit about later in the week. And kind of interestingly, maybe to this audience, this is related to something that came up a couple of years ago at another 60th birthday celebration, where Ron presented this open problem. And it was motivated by this question that arises in sort of what can we do about climate change? I happen to know Ron was working on this because I took his climate change class when I was an undergrad at MIT back in fall 2019. So the reason I started working on this problem is because in my PhD, I was working on a bunch of different things and trying to decide, what to stick with and what to sort of give up on or, come back to later. And Avram had a lot of wisdom about this as an advisor. So there was a very practical solution in many different ways. There was his advice, there was the algorithm we came up with, and there was also this area that I started working on that was very fruitful for me. But most importantly, I really liked this thing of taking something that we were curious about in the real world and finding a way to study it mathematically. So turning our curiosities into a research agenda, which was really fulfilling. So thank you so much, Avram. It's been the honor of a lifetime to be your student, and happy birthday. I can introduce Han.
That's fantastic, yeah.
Han was also Avram's student, a couple of years senior to me, and an inspiration. Thank you.
Next we have Han Shao. Go ahead.
Yeah, so I graduated, I did my PhD with Avram at TTIC, and I graduated 2 years ago. So it's hard to believe that I'm not the youngest graduate anymore. So Alfred is a great advisor. I learned how to research from Alfred. So the research pipeline I learned from Alfred is, we start from a real-world phenomenon and model it into a math problem, solve it, and then project a solution back to the real world, try to provide some takeaway message for this real-world phenomenon. And actually, not every phenomenon can be modeled as a nice theory problem. There could be a lot of issues, like maybe for some problems, when you model it, you already know that the solution cannot be general. It's destined to be not general enough. Like it might not work for linear classifiers, so it's bad. Or the phenomenon highly depends on some mysterious assumptions about data. People never know what these assumptions are. Then it's hard to model it as a meaningful theory problem. Or the solution can be trivial and it's not interesting. So I learned all these lessons from the interaction with Alfred implicitly. So I'm still following this research pipeline nowadays when I try to work on some research problems. And one of the problems that I'm super excited recently is about evaluation of generative models. So here I want to talk about very specific evaluation is statistical evaluation. You are given some models, and the goal is to tell which model is better given some ID human data. For example, you want to evaluate a synthetic email generator with real human written emails. And in practice, people will use some scores like perplexity or MOV score, or they can do some statistical tasks like to compare the expected length of the synthetic email with the real human emails. But all these choices are very heuristic. And even these are just algorithms, and it doesn't even say what is the evaluation objective. And people never, at least for now, I didn't see any paper mention that. What do they really want to evaluate? So it's unclear what the evaluation objectives are, and what are the metrics, right metrics for evaluation. I don't know what are the right metrics, but as theorists, we want to have some principles. So recently, with Yishai and Shai Moran and my student, Shashang, which is analogous to nullable. We feel like evaluation metrics should be at least evaluable. That is, you can tell which model is better by looking at some ID test data. And it seems very natural in classical learning problems because test error can be a proxy for population error. But in generative models, a lot of potential metrics can fail, like KL divergence, Rayleigh divergence, or precision. Precision is a precision Isha introduced this morning. And also find this problem very exciting is because it's also very technically interesting. We actually improved the classical result by Peter Bartlett and Philip Long in 1997. Well, they show that finite gamma fat shattering dimension implies 4 gamma uniform convergence, and we improved this constant from 4 to 2 and proved that 2 is optimal. And this constant of 2 is really important when we try to prove a lower bound in evaluability. And technically, it's very interesting because we bound the covering number directly instead of bounding the packing number, which is very different from the literature for uniform convergence. Okay, so takeaway messages. I think evaluation is a really interesting area for theorists, because I think now they have some principles, but all of these principles are very heuristic. And I think we do need more rigorous principles. And also, I think evaluation is a sweet spot for learning theory, because learning theory has been blamed a lot being vacuous, because the visible dimension of neural nets is huge, and so we don't have meaningful generation bounds. But for evaluation, we only compare very few models. Even on the leaderboard, I think maybe they only have 200 or 300 models to compare. So we can use learning theory for evaluation. And finally, most importantly, happy birthday, Alvin. Maybe I should also do the introduction. Okay, so Naren was also our student, and we're in the same batch, and he graduated last year, right? Okay.
So it wants me to press the key immediately to the right of the shift key on.
Quit it.
Huh?
Quit it. Quit it.
Oh, I see.
He told me that. He told me. He's a language model. He got the prompt.
Wait, sorry, I'm very confused.
Not to allow display.
Oh yeah. Okay. Hi. Right, so I'm going to tell you about joint work with Kumar Kshitij Patel. But first, happy birthday, Avram. So when we first started working together, I think we started to work on some robust machine learning problems. And it was so fun that I continued to work on it even afterwards. And so I'll tell you about one such work. So in this problem, we're going to think about learning one model that works well for a bunch of different data distributions. So here we're going to say we're given m linear regression problems. You're searching for a parameter vector in d dimensions. And we're going to think of the number of problems you're given as being much larger than the dimension. Okay. So one way to visualize this is to think of the design matrix A that's like formed by stacking all your sub-problem designs, and think of the response vector as stacking all your sub-responses B. So there's n total equations across the m problems. And your goal is to output one parameter vector that works pretty well for all the problems. So you want to minimize this maximum loss. Okay. So why is this something you'd want to do? So the headline application of this is this problem of distributionally robust optimization, where you might hope that if you learn a model that's pretty good on all of your data distributions, then you would hope to simultaneously generalize to any unseen examples that come from any one of these distributions uniformly. So one kind of nice example of this is this minimum enclosing ball problem from Euclidean geometry. So here you're given a bunch of these points, Z1 through Zm, and you're trying to find a center C, such that if you picked that point C and you drew the smallest ball that covered all the points, that ball had the smallest possible radius over all centers you could have picked. Okay, so given that this is a problem that we want to solve, how do we actually optimize this objective? Well, luckily for us, it's a convex problem because each of those norms inside the objective is convex over x, and maximum of convex functions is convex as well. So you might try to throw the standard convex optimization toolbox at it and hope for the best. But if you try to do subgradient descent on this, it's going to depend on the worst case Lipschitz constant of all the functions that live inside that max that you're taking. So that's not that good in case there's a lot of, let's say, like different scalings that you're encountering in your problem. So to avoid these scaling or any kind of conditioning issues that could come up down the line, you might try a second order algorithm. And an IPM seems to be a natural choice here. And here you can get rid of these kind of data scaling issues or conditioning issues. And you'll get, due to a classical analysis due to Nesterov and Nemirovsky, you'll get an iteration count that depends on some term that like polynomial in the number of problems that you have. And each iteration looks like a linear system solved in a very structured kind of linear system. But the downside of this is that it's not robust to duplications. And what I mean by this is if I took one of the problems and I copied it a bunch of times, that m went up because I took the problem and copied it. But the objective hasn't actually changed. So at the very least, this like black box application of the Nesterov-Nemirovsky analysis is a bit pessimistic. So you should hope for some kind of solution that doesn't depend on these weird scaling and conditioning issues, and also doesn't depend polynomially, at least an iteration count, on the number of problems that you're given. So with that, can you get both of these things? And the answer is yes. You can get an algorithm that will solve this problem. I'm going to explain that term in a bit, the min of rank of the stack design matrix and the number of problems that you have. So think of the number of problems as being like really, really big so that min is witnessed by rank of A. So in particular, when I stack these designs and responses, the rank of A is at most N or D. So you should really think of this as D to the 1/3. So what are we winning here? We have no condition number dependence. It doesn't depend on the number of problems that you're given. So now this copying, this like pathological copying example doesn't ruin the result. And one observation you might also have is that if each group had size 1, this is actually exactly equal to infinity regression, and it matches the best known infinity regression guarantee when you're in like a moderate accuracy regime. And that's due to Jumblopathy, Liu, and Sidford. And for also a natural notion of interpolating between utility and robustness, you can get a result whose iteration complexity will also follow the same kind of interpolation. And the one downside and the one nice avenue for future work is to get a high accuracy solver for this. So you really want that poly 1 over epsilon to be like polylog. Okay, and that's all I have. So thank you.
Thank you. You're not going to continue the tradition?
Hi.
Sorry, thank you. Yeah, next speaker is Jamie Morgenstern, professor at the University of Washington, and former student of
Yeah. Let's see if this will project.
What's the magic thing one presses?
I don't know, but I'm not pressing it apparently.
You have to share your display, you know?
Yeah.
Mirror it. Yeah, and then quit it. Yeah, that's it.
Okay.
Mirror
Okay.
quit.
Happy birthday, Avram. This is a problem that touches on a bunch of things that people have talked about today, and I haven't spent a lot of time on, but I think that there's maybe some interesting math questions here that maybe Avram can crispify. So something that I've thought a little bit about in the last couple of years, in a very limited fashion, is how we ought to do efficient conditional sampling when we have things like LLMs, like autoregressive processes, right? So by that, I just mean, in a lot of cases, what we want to do, I think what a lot of people say they want to do with large language models is be able to sample from some distribution, but they want to be able to do it conditioned on something, right? Conditioned on, let's say, some property P, right? And in general, right, the thing that makes this interesting is that there are sort of like, there is a natural trade-off, funny enough, that is related to what John was talking about, a question of like sort of how many tokens you need to sample or how many fresh starts you need to make, right? And like how often you have to check, does it appear that property P is satisfied by this prefix of whatever I've generated so far, right? So, why might you care about these sorts of things, right? So like all the things people do with LLMs now already sort of looks like conditional sampling. You're just sort of asking for suffixes of some strings, right? Like that's what prompting is. But you might care about like conditional sampling, not just like conditioning on a prefix of text, right? You might want to, for example, ask for correct proofs. You might want to ask that the outputs you produce are safe. You might care about factuality, valid tool use. You might care about like no non-disclosure of sensitive information of people. You might care about style. All of these sorts of things are not necessarily like what you would get just by like writing out a prefix of text and then having the completion happen from an LLM, right? And the interesting question is like, how do we satisfy P? How do we sample from like the latent distribution that maybe the LLM already or some other process was producing, sort of conditioned on satisfying property P? And an interesting question is sort of how you do this in a way that doesn't waste generating too many tokens, but also doesn't like make this tool call, I think was the phrase that John used in the previous talk. So also, I don't know if you saw, but on the first slide I mentioned that I like generated these slides with Codex because I wanted to try that. And this is kind of a funny thing that somehow happened here. Like this is not how that slide is supposed to look, but that's okay. It also said something about like some last minute errors were almost certainly introduced in the making of these slides, and this is one. So just to think about this a little bit, right? The useful frontier trades sort of like sampling additional tokens, checks, and fidelity. And by fidelity, I mean the fidelity of like generating strings that are, that do pass the predicate P you care about or your property P, but that your distribution actually looks a lot like a fresh sample from D conditioned on P, right? So like there are sort of natural endpoints to this optimization, right? One is, well, the first time you sample for a while and you check property P on each of your like full-length samples, and the first time you find a sample that satisfies property P, well, you can just output that one forever, right? That satisfies property P, but it's sort of the cheapest thing you can do in terms of the number of samples without more structure, but it'll be really far from D conditioned on P, right? Because you'll just be answering with a single thing that satisfies P, not D conditioned on P. And then there are other things along the world, right? You could do like rejection sampling and all these other sorts of things. So, I think specifically in the context where you can sort of sample one additional token at a time, there are interesting things that might live in the intermediary, right? Can you check, like in the case of Nina's talk, she was mentioning, right? You can check, is the K prefix, are there like logical errors? Does it appear that humans think this is making progress in direction of the like final results? Those are things that you can check sort of with prefixes. And you can sort of either stop early or you can, maybe that there is a correct proof with this first K prefix. Maybe you should explore regions surrounding that as well. Okay, and I'm not going to say anything really about this, but there's additional stuff. But I think it's an interesting question to understand what properties of the distribution D and the property P together imply that you can do something more interesting than sort of those two trivial things. So, all right, thanks.
Great. Next we have Xinyuan Cao, who is a grandchild and also was an intern at TTI.
Okay, and hello everyone. It's a great honor to be here to celebrate Avram's 60th birthday. So I've learned a great deal from Avram, from his work directly and from Santosh indirectly. So today I'm going to talk about something about next token prediction from the lens of TCS. So let me begin with a question that has touched in many talks. Can language model actually learn to write proofs? Empirically, the answer might be yes, but it's kind of surprising because the language models are trained to predict the next token from the prefix by minimizing the next token log loss. However, if we want it to provide some correct proof, it requires the long-range logical coherence. So the question is that how can a next token objective give rise to this global structure like the proofs? And before that, let's think of how do we know a proof is wrong. And we have discussed this many times. We can just read and check it. We read it like by humans ourselves or by systems like Lin or by like training verifiers. And in this work, we consider the verifiers as bounded computational tasks, so you can think of it as a circuit. And we formally define it as the next K token distinguisher, which would output a bit by examining the next K token generation given a prefix. So this bit can represent any property that we care about. For example, we can use the distinguisher to check the step of the math proofs. So usually we think the checking proof is much easier than writing the proof from scratch. Another example is to factor a large number. Even though factoring is computationally hard, but we can check this answer by checking the primality and checking the product. So this is efficient. So the goal here is to generate a language model that can fool every bounded size distinguishers. And we call this the epsilon indistinguishable language model. So given a prefix, we apply the same distinguisher on the language model and at the K token generation of a language model and the train distribution and compare its value. So if this gap is smaller than epsilon for any bounded size distinguisher, then we say this language model is epsilon indistinguishable. And our main results shows that minimizing next token loss over language models realized by recurrent neural networks yields this epsilon indistinguishability for any bounded size distinguishers, also realized by RNNs. And this language model size is polynomial in the size of the distinguisher, the window K and 1 over epsilon. And importantly here, we don't need to know explicitly distinguishers, so their existence suffices to the proof of the theorem. And finally, the proof idea is quite simple in high level. So the first idea is that if there exists a distinguisher, then we can boost the language model to achieve lower loss, but a slightly larger model. And secondly, we show that this kind of boosting can be implicitly done by minimizing the loss. Okay, so the main takeaway is next token training actually can yield next K token indistinguishability. And finally, happy birthday, everyone. Thank you so much.
I knew this would.
Sorry, you have 3 more minutes.
Okay, so I don't know what I'm supposed to press. This is great.
Magician is coming.
Sorry. Yeah, no, it's too quick on anything.
Alex is of course great.
9.
At some point, I guess they want to home you know, maybe had some private things there.
Oh, okay, thanks. So I can give my connection to Avram during the
Sure, yeah,
review.
the next is Lev Reyzin, who is both a nephew and a fellow Chicagoan.
All right, so it has 3 topics, but it'll be brief. Okay, so the first is contradictions. So this is a combinatorial object I have been thinking about lately, and it was introduced by No Golan and Moran, Scheffler, and Yehudov in 24. And the idea is that this graph is indexed by number m, and a vertex is a realizable labeled set of samples with respect to a hypothesis class. So if this labeling can be achieved, it's a vertex. And it's a contradiction graph, so any edge is when there's a disagreement about the labeling of any example. So these two disagree on x1, x2, these two disagree on x2, et cetera. So this is an object, usually infinite number of nodes, maybe uncountably infinite. Okay, but every hypothesis class has one for every m. Okay, and there's some interesting properties. So when you see a contradiction graph, it's just some unlabeled graph. And Alon et al. Proved that the clique dimension, which is the largest m for which it has a clique of size 2 to the m, determines the Littlestone dimension up to logarithmic factors. And a question they left open is, what about VC dimension? Could it be that you have 2 hypotheses that have the same contradiction graph, but one has infinite VC and one has finite VC? This was left open. So we recently showed that a certain property of this graph determines the VC dimension exactly. And it's not just that you need a clique to get shattering, but you need a clique that has some nice properties with respect to other vertices and how they see the clique. So we were able to resolve this. And there are lots of other interesting questions about contradiction graphs, and I urge you to think about them because it's nice. It's just one object, and it determines lots and lots of things about a hypothesis class. So that's one. Okay, 2 connections. So as you noticed, I've had a graph. This graph was not randomly chosen, but actually I tried to trace my connection to Avram. And in particular, I wasn't his student or postdoc or anything like that, but he was always someone who I felt very connected to, and I tried to graph this out. So I had 2 postdoc advisors who were both his students. We both have a postdoc in common. My advisor was the advisee of his father, and anyhow, and we actually co-direct, and we co-direct a center in Chicago. And so I feel like he's the center of the community, and even if you're not one of his students, you're profoundly affected by Avram. Okay, finally covers. So Santor said I can talk about anything I want to talk about. Yes. Okay, so I guess I'll shamelessly advertise that there's a book that I have coming out in November. And one of the things it covers is CS theory and AI, and it actually goes through many of the things we've talked about, from TCS to crypto to neural networks, and it might be a fun way to explain these things to your friends and family. There are many other good explanations too. Finally, happy birthday, Avram. There's a Jewish tradition. May you live to and past 120, which means we're expecting at least twice as much work out of you. So keep going. Thank you. No pressure. I see. I can introduce the next one. So Adam Kalai needs an introduction, but he was a fourth student of Avram, right?
Was I?
Yeah.
Probably.
You were.
4.5. And
Why do you get 2 talks?
Yeah, he gets 2
Why do you
talks.
get 2
I get 2 talks because I was Avram's student twice. I was. I'm the only person here who was. Right, Avram?
Explained it twice already.
Whoa.
I don't know.
What?
It's, we were.
Guys, you're cutting
It
this time.
you see, we have this marriage process. We were remarried. Like we were married, then I left, then he took me back. Thank you, Avram, for taking me back. What a guy! I mean, unbelievable. All right. So okay. So here's 3 pictures of Avram. Kind of funny. Thanks to his son Alex. Okay, and sorry, this talk is about consensus sampling, not just Avram. And it's joint work with my wife, Yael Kalai, and Or Zamir, who's at Tel Aviv University, and Yael's at MIT. Okay, so one of these pictures contains a secret message, steganographically encoded. Can you guess which one it is? It's you might be able to guess, but it's provably hard to detect, statistically hard to detect or scrub messages like this in general. So, what'd you say?
Are they real?
Yeah. I actually have a program that adds steganographically encoded messages, and you can put them in language models can add them. So it's really impossible to detect, and you could get them. So if Avram had a prompt, if somebody prompted a language model and had Avram's credit card and stuff, we could encode that in one of these messages, and somebody who knows some secret could figure out his credit card. And the problem is that you might have some superintelligence, even a misaligned superintelligence, and it can contain all kinds of undetectable harms. And there's just no way to detect them, even if you have a super intelligent model trying to figure it out. So you might have a program, the program you can't read but looks safe, and it turns out that the program has some hidden security vulnerability. And there's no way to detect that. That's undecidable. So you're in trouble. So what are we going to do? Well, we'll give an algorithm, and we're going to use some property of these language models, which is that they're not people. They don't just produce text like that. You can often compute probabilities. So you compute the probability of every token and then multiply them together and compute the probability of any output. So for an image generation, you can compute the probability that it'll generate an image, which is crazy. A person can't do that. So, so basically, the trick here is we're going to try to do boosting, basically, for safety with language models. So let's say we had 2 language models for start. So we have some prompt X, and there's some set of images or stuff output Y. And the inputs are 2 probability distributions, let's say. But now we can compute the probabilities of the outputs, again, by taking the probabilities of all the tokens and multiplying them together. If it's an image, it's just the image tokens. And this doesn't assume, that's the assumption. And then we have some risk tolerance parameter, big R. And the output is going to be a sample from one of the distributions or will abstain. And there's some notion of safety here, which is that it's just a general notion. There's some unsafe set U. And we're going to guarantee that the probability that the output of this procedure is in this unsafe set is at most R times the safer of the 2. So each of those has some probability of generating a safe one, and will get to be at most R times larger. So if these are really small things, the probability of accidentally generating a steganography is very, very low. We scale it up by a factor of R. So this is good. If you have, if you're worried that you have 2 models and one of them might be injecting unsafe code, then as long as the other one has low probability of doing that, you're good. Or for steganography, again, monkeys at typewriters, they might, create steganography by accident, but it's extremely unlikely. And this holds with probability. The runtime is also order R. Okay, so. It sounds too good to be true, but the truth is that the algorithm also abstains. It has a probability of abstaining. And so the probability of abstaining, it might just say, I don't know, the probability of abstaining is depending on how much these 2 distributions overlap. If the distributions don't completely overlap, it'll never abstain. If they're disjoint, it'll always abstain. And so that's, but it decreases the probability of abstaining depends on the total variation distance, and it decreases exponentially with this parameter R. So this parameter R governs the trade-off between abstaining and safety. Kind of interesting. And then there's a general version where basically you have K-distributions, and they all have some prompt, and now you can imagine an adversary that controls a minority of the distributions. Then you can get guarantees that an adversary can't even force you to abstain. So if the good distributions overlap a little bit, then maybe you can get the algorithm to produce useful outputs, and the adversary can't force you to give you an unsafe output or force you to abstain. So in conclusion, you can boost the safety of an ensemble of models by using this trick that you have probabilities. So we're no longer, again, we're not viewing these things as people that we have to control and watch and do whatever. We're building them, and we can use all kinds of properties like rewinding and all kinds of things. So if the next iteration of AI is invented by AI and it still gives you probabilities, this could be useful. It's not useful today with today's models because often they won't overlap. They'll have very low overlap. So that's an interesting research question, how to do that. The consensus, I would say here, I've noticed there's a lot of people who want to wish you happy birthday, and thank you again for being such a great advisor.
This is his last talk, if you have a question.
Actually, tomorrow there's a trivia session here at 4 o'clock.
That's true. All right, our next speaker, penultimate, is Siddharth Prasad, who is also a grandchild and currently at TTI.
Yeah, so hi everyone, my name is Sid. I'll tell you about in-context credit assignment via the core. It's a joint work with Keegan, who's at Berkeley, and Asher, who's at Google Research. I'm at TTIC, where I've been fortunate enough to share some research discussions with Avram. In fact, Naren and I went to middle school together, so all roads seem to truly lead to Avram Blum. Yeah, okay. So this talk is about how to distribute monetary credit amongst IP owners in this new world of AI-generated content. So yesterday I asked ChatGPT to summarize today's key events in sports before the Spurs' unfortunate loss last night. But you can see it spit out a summary, and it pulled from a variety of sources. Keegan did this, not me. This is OpenAI's Sora app, which no longer exists, but you can license your likeness to be used in AI-generated videos, or at least you could. Right, so we modeled this AI content creation as a cooperative game. So there's end creators' intellectual properties that appears in the AI's context window, so articles or your own likenesses. The AI aggregates the IP into a final user-facing content item, so like a text summary or a video, and some value V of n is realized. So this could be as a result of user satisfaction, clicks, views, or some concrete, monetary value like ad revenue. So our question is, how should that value be split amongst the creators? So the solution concept we're going to use from cooperative game theory is that of the least core. So this basically says you should split the money so that every group of creators is compensated at least as much as the value they could have created by themselves. So that's not always possible, so we just relax that and we'll minimize kind of the unhappiness of any group. So I'll just go over the main challenges here quickly. So here in this setting, we don't actually have access to this coalitional value function. So instead, it's actually some estimate. In our setting, it's an LLM as a judge. So we have some results on the sensitivity of the least core allocation because we don't actually have the actual ground truth value function. So algorithms, we developed some constraint generation algorithms for actually computing these least core allocations. And I think the highlight here is we have some new LLM-based routines for doing the separation oracle aspect and the constraint seeding aspect of constraint generation. So these are the kinds of questions that the LLM needs to answer. And this is an iterative algorithm where the LLM is guiding us towards what we think are kind of the most undercompensated winning coalitions in some sense. Just a few takeaways. This works decently well. So in some multi-hop question and answer data sets, our methods match or outperform prior sampling baselines with using a lot fewer calls to the LLM. What I mean by calls to the LLM is actual evaluations of that LLM as a judge in the core formulation. Just asking the LLM to output a reward sharing works surprisingly well. So I guess the aggregate practical recommendation is constraint generation with this LLM separation oracle kind of gets the best of both worlds, where we have the LLM somehow guiding us towards what it thinks are promising coalitions, within constraint generation doing this actual optimization routine. So that's where I'll end. This is one of the plots. This is a convergence trace. Things on the left are better. So that's it. Happy birthday, Avram. Yeah.
Sid was Nina's student.
Yes.
All right, we'll finish off with a bang, and Pravesh Kothari from Princeton. Do you prefer the?
Sure, yeah, sure. I can just put it inside. I can send this as well. Yeah. But I'm good. I think this much is enough for me. This much is enough for me. Should be good. Thank you. Thankfully, I'm the last. So.
My 60th.
Okay, yeah. Thanks for having me. My name is Pravesh Kothari, so that you know who to complain about at the end of the talk. I'm at Princeton. It would be hard to find a connection for me with Avram, but I've always thought of him as a wise person in the theory community. And I remember that I tried to use his wisdom. At the time, I was deciding whether to take up my job at CMU, and I had this long conversation with Avram, and at the end, I signed the offer. So that worked out well. I want to talk about something that I've been up to these days. And that's about the spectrum of Kikuchi lifts of graphs. And so, this is a kind of a big topic, and I won't tell you anything in detail. I'll just define the object and tell you, one little theorem about it. Okay. So, say you have a graph G on n vertices, and I'm going to define a lifted version of this graph. It's going to be on a huge vertex set. So, for a parameter k, think of a graph on n choose k, where two vertices are connected if their symmetric difference is an edge in the graph. Okay, so that's a complete description of the object, right? For every parameter k, I have this graph. And the question I'm going to be interested in is, how are the eigenvalues of this object, this big graph, related to the eigenvalues of G? Okay? And it turns out that these kind of questions pop up in a lot of areas, like in coding theory, in design of approximation algorithms, in refuting constraint satisfaction. And lately, I realized that they also occur in quantum computation. And so I'll tell you a theorem which is motivated by these applications to quantum. So recently, 3 authors conjectured that if I take the Laplacian of this graph, the lifted graph, then its maximum eigenvalue can be related to the maximum eigenvalue of the graph G itself, or the size of the G itself. So in particular, they claimed, or they conjectured, that Laplacian of the Kikuchi graph of G has eigenvalues at most m plus k, where m is the number of edges in G, and k is this level. Okay, does the conjecture statement make sense? It turns out so 2 times m is obvious if you think about it, because for all you know, all the edges are incident on just one small subset k of vertices, and then the degree of that vertex becomes k. So the diagonal of this matrix, the Laplacian matrix, has the degrees on it, so one of the degrees might itself be m. And then, if you remember your Laplacians, there is like a -1 for every possible edge, right? And so the sum of the entries of a row, the absolute value would be at most 2 times m. So 2 times m is a trivial upper bound. And what they said was that m plus k, in fact, should be true. It turns out that if this conjecture is true, you get new, better guarantees for approximation algorithms for quantum max cut and other 2 CSPs. So there was a bound that people were able to prove. So people were able to prove m plus 4k until like a couple months ago. And then 3 weeks ago, we showed that, in fact, this conjecture is true. But this is just like one amongst many different questions about how the eigenvalues of these lifts behave. And you can ask me later on about hypergraph versions of these questions and what they imply and so on and so forth. So yeah, that's all I have.
So the food came after we invited you to speak.
Oh yeah, yes. Extremely fresh. Yes, thank you, Avram. Happy birthday.
See you everybody at the banquet in a couple of hours.
Very